Hi everyone, I'm Paul Eizenhöfer and I'm presenting here on behalf of Sarah Falkowski. But at the same time, I'd like to highlight the synergies that we have here present at the Glasgow Centre for Sustainable Energy, coming from a very earth scientific background, but clearly seeing the overlaps between projects that concern energy and specifically geothermal energy. So here in this project, um, I will be talking about long-term thermal history reconstruction and landscape evolution modeling to explore the geothermal potential of rocks. Both Sarah and I are from the School of Geographical and Earth Sciences, and this particular project has been funded under Sarah's lead. So before we talk about long-term history and the evolution of landscapes and so on, we use thermochronology, and specifically we use low temperature thermochronology. And what does that mean? What is that? So we can extract from rock samples crystals, and in this case, usually it's zircon or apatite crystals, to measure the thermal history of these rocks that I've seen over geological timescales. So these measurements concern the evolution of the Earth's crust at a certain range of temperatures, and these are 50 to 250 degrees Celsius. And here at the University of Glasgow, we have a brand new lab, also state of the art and leading worldwide and in the UK this kind of effort. So we look at timescales here that are on the geological scale. So talking about hundreds of thousands to hundreds of millions of years of timescale. However, anything that evolved over these timescales affects us today in the present. And this kind of approach, low temperature thermochronology, has a wide range of applications in geosciences, but also beyond that. So, for example, in engineering, assessing geothermal potential across regional scale landscapes. And to give you a bit of an understanding where Sarah and I are coming from and how we use this kind of data set. So looking at this fairly complex figure that shows the combination of thermal models, numerical models, and the application using empirical analysis. So what you see here, these dots, these are measured thermochronological ages. So using the low temperature thermochronology method, and when you look at the lines, these are our numerical models where we fit the data that we observe in nature, in reality, with those in our models. And then at the same time, we can then reconstruct the present day thermal field in the crust. So that's what you see at the bottom here, where you see on the y-axis, you see depth, and you see on the x-axis the distance along a certain region. And this one is an example of the European Alps, where we successfully were able to reconstruct the thermal field of the present day. And that's confirmed by not just only reproducing the data that we see concerning low temperature thermochronology, but also looking at the surface heat flux that has been measured along the Alps, where you see the red dots here aligning rather well with our predicted surface heat flux from the model. So in essence, we are able to use now this kind of geological record to create at a regional scale a thermal field that then becomes of interest to geothermal energy prospects. But we can also go a step further. So this is a publication that we just recently published in Science Advances, where we use now the reconstruction of that thermal field, which is then linked to the reconstruction of the tectonics in an area, and then feed that into so-called landscape evolution models. So we can recreate now the landscape, not just over geological timescales, but also reproduce the present day landscape. And that's something that we are planning to do for Scotland as well. So looking at the thermal record of the rocks across Scotland and then reconstruct the thermal field, the thermal evolution, to reach a solution that represents the present day solution and the present day thermal field, and then try to reconstruct the evolution of the surface of Scotland. And this is an example where we applied exactly these techniques to the Andes. And now to focus a bit more on the project that Sarah is leading, where she's assessing the geothermal potential of Scottish granites by establishing their long-term thermal history. It's funded by the Royal Society, and the task primarily in this project is to collect samples along the Scottish Highlands. And the questions asked in this project are what is controlling the differences in the Pluton's radiogenic heat production? Because the Scottish Highlands and Scotland in general, they are dotted by these granitic plutons. So we want to know the age information, we want to know their geochemical evolution, and then also the level of erosion exhumation they've experienced to then also go back and assess the geothermal potential of these granites. And here's just giving you an example of where we collected samples already. So the project, the sample collection process that has been completed. All the dots that you see here, these are samples collected from the field. And here you see some images of some of our field trips that we've conducted. So some of that field work was linked to the collaborations that we have with THERMOCAL and also collaborations in the Glasgow Centre for Sustainable Energy. And on top of that, now we start advertising projects in collaboration with our colleagues from engineering, where we look at assessing the geothermal potential of Scottish granites by, again, establishing their long-term thermal history. That's an IAPATUS project, and it's open, this competition. So we encourage anyone interested to apply for this. And this is supervised by Sarah, colleagues from the Geological Survey, as well as colleagues here at the University of Glasgow, including myself. Thank you very much.